Today's lesson is in section 4.3. We're talking about logarithmic functions. Now, a logarithm function is denoted as log of x base a equals y. Now, in translation into an exponential function, that means that the a is actually the base value that has the exponent of y. So the y is actually representing this exponent over here. The a is this base, and the x is what a to the y power equals. Okay, so that's how the two are connected. So one of the skills or things that we use or in this process with logarithmic functions and exponential functions, we actually interchange them to be able to either like solve for something or to put it in a form that maybe makes more sense at a certain time. So example 1 wants to know or wants you to change whatever you're given into the other form. So for letter A, we're given logarithmic form, so I want to change it into exponential form. So that means that 10 is my base that has a power of 5. So it's like I go over there and bump it up, and then that equals this 100,000, which we know to be the case. If we take 10 to the 5th power, we get 100,000. Okay, so then that would be their answer that they're looking for. Okay, now if you're in exponential form and they ask you to change it to logarithmic form, then that means that this is the base for our logarithmic. So I move this to this base, and it's moving over there to this number. Okay, and I'm left with the exponent of -3 on the right side. So then log of 1/8 base 2 is equal to -3, because 2 to the -3rd is 1/8. Okay, so now we want to be able to use that to our advantage. So if I'm going to evaluate, I can set these equal to a value of x or y, whatever variable you'd like, and then use your changing of to the exponential form to help you solve. Because looking at log of 64 base 4 doesn't quite make sense at that given moment. So if I move 4 over, then 4 to the x is going to be equal to 64. Now it makes a little bit more sense. Okay, so 4 to what power gives me 64? Well, if I have 3 as my exponent, 4 to the 3rd equals 64. So that would be my answer. Okay, same thing with log of 625 base 5. So I move the 5 over, 5 to the x equals 625. So then 5 to what power gets me 625? I believe, because to the 3rd power is 125, I believe the 4th power gives me 625. And then that would be my answer for these. Okay, so super easy. Example 3, we want to graph the following functions. F of x is equal to log of x base 2, and f of x is equal to ln of x. Okay, now one thing that I want you to note is that anytime I have an ln, all the properties work exactly the same for my logs as they do for ln's. Okay, so all properties work. They're just a different type of logarithm. This one has a base of e. It's not written there. It's just assumed that the base is e. That's why it's called a natural log, kind of like our natural exponential functions. That's where that gets, or that's where the word comes from. So if it has a base e, then that's what, when I switch it around, it'll have e to the x equals something. Okay? So for both of these, I want to be able to change them into exponential form. So first let's get rid of the f of x and write y, just so it's easier to write. Okay? Now I'm going to change them to the other power. So the 2 is my base over here, so 2 to the y equals x. So now you're almost flipping the operations of x and y, so their roles change. So now you're plugging in y values to find x values. Same thing here. I'm going to move this base of e over, so it's going to be e to the y equals x. So now when I find these, I don't actually plug in anything in for x, I plug in stuff for y, but the same properties hold. When I'm graphing exponential functions like I do before, I want to set them equal to 0. So both of them are just y, so then that starts with 0, and then go one less, one more, and I plug them in. So 2 to the negative first, 2 to the 0, 2 to the first. E to the negative first, e to the 0, and e to the first. Okay? So 2 to the negative first is 1/2. 2 to the 0 is 1. 2 to the first is 2. Okay? A little harder. E to the negative 1/1 power is going to be 0.37. E to the 0 is 1, because everything to 0 power is 1. And then e to the first, we already have that approximation, is 2.72. So now I can graph. Okay, just to use different colors, let's use blue with this one. So -1, now this is going to be the funky one. Oh, let's make this a little nicer. Okay, there we go. Go back to the blue. So x is 1/2, y is -1. So there would be my point here. 1, 0, and then 2, 1. Okay, so my graph will look like that. And then let's go with green. So then for the other function, so -1 is 0.375, 0.37. Right there. Still 0. And then 2.72. So they're about the same for this example. Okay. Now log functions have asymptotes too that we want to approach, but they're more vertical. So here, this would be your asymptote, so it would be an x equals 0 line for it. So I'm not going to pass that at all, just like we did for the exponential functions when they were to start exponential functions. Okay, because remember, even though we're using exponential function for them to graph, we're almost taking like the flip of it, because logs and exponential functions are inverses of each other. So when I change it to 1, like because the x and y are in different positions, it's, if I wanted them to be normal, then we could switch them, and then that would be the inverse. So e to the x equals y would be the inverse of e to the y equals x. Okay? So that's just the difference between the two. Now there's several properties that I want you to go ahead and write down. We'll talk through some of these here. But basically they're just overlap between logs and ln's, which is the same. So for log of 1 to any base, same as ln of 1, because it's base e, it's always going to be 0. Okay? That's just saying that if I switch it to exponential form, that'd be a to the 0 power is equal to 1. Same thing here. E to the 0 power is equal to 1. Okay? Log of a base a equals 1, and ln of e base e is equal to 1. So the reason why that works is that I have a to the first equals a, or e to the first equals e. So for those, they're just stating the obvious. A is equal to a. They're just stating what the exponent is, which is 1. Okay. Now, to go along with that, so no matter what your exponent is, so like here, let's say you have just a random exponent. Right there. Okay, so a to the x, if I switch it to exponential form, equals a to the x. Okay, which is a fair statement. The x's should equal each other. Same thing with this one. If I switch it, e to the x equals e to the x. Okay? And then the last one is kind of the reverse for this one. So if I switched it to log form, because this is my base here, so is e here, so then log of x base a is equal to log of x base a. Same thing here, ln of x is equal to log of e base x, which I'm showing right there is the same thing. Okay? Now, let me use a different color actually. So log of x base 10 is called common log. That's the logarithm button that you have on your calculator. It's in base 10. So anytime we write log of x, it means that its base is 10. Okay? And then same thing here. This is saying that it's just natural log. Okay? Which we've already talked about. So ln of x means that it has a base of e for a log. And then here showing the switching. So you can go from ln of x equals y to e to the y equals x, and just changing it to exponential form just like we did for the other ones. Okay? Have fun. Bye.